Welcome back, folks. We're going to look at the other type of divider. So we worked with voltage dividers, and then we built that up to turn it into Kirchhoff's voltage law. We're going to take the same approach with the current divider. It shows up just as frequently as the voltage divider, and that really we're going to see why when we get to the theorem section of the course. But for now, we're going to just kind of do the basic current divider. It's a pre-canned formula. I don't like pre-canned formulas. I like you to be able to go back to Ohm's law, KVL, and then the law that we're going to build up out of this one, which is KCL, Kirchhoff's current law. And I like you to go back to those, but this formation of circuit shows up so much that it's good to have some intuition, and it's good to be able to apply the formula quickly and accurately. Okay, so I've got this drawn already for you, and we'll start from here. What we want to do is figure out how this 3 milliamps coming in from the source is going to split between these two branches, and these two branches are in parallel. Okay, with the voltage divider, we needed to make sure things were in series. With the current divider, we need to make sure that they are in parallel, and they are in fact in parallel. You should have asked yourself already, do they share the same two nodes? And in this case they do. There's a node on the top and there's a node on the bottom. The current supply isn't always in parallel with them. It's more important that we know the current going in to two parallel branches, and we want to know how it splits between those two branches. So let's figure it out, and we'll do it numerically, and then we'll build back up symbolically so that we can find the form of the current divider that we're looking for. Okay, with the current divider, we can take this and we can say, yeah, those are in fact in parallel. Okay, so I can redraw this circuit by combining those two things in parallel into a single resistor. Okay, now I've lost those individual currents, and that's going to be okay for the time being. What we're really interested in is the voltage across that parallel combination. So this is going to be 5K in parallel with 10K. All right, and let's grab a calculator and figure that out. So we have 5K, and the way I like to do this is to invert that, add to it 10K, and invert that. Go ahead and hit the enter button and then invert that answer. So we get 3.33K. Okay, 3.33K for that parallel combination. This is still 3 milliamps. All right, and what we're after from this simplified circuit is the voltage here. So if I know the 3 milliamps is flowing here, it's going to flow down, and I'm going to find the voltage here by saying that voltage is 3 milliamps times 3.33 kilo ohms. Okay, now you can probably do that one in your head, but let's abuse the calculator a little bit, and we take that 3.33 K and we multiply it by 3 milliamps, and we get 10 volts. Okay, so we know we have 10 volts across that parallel combination of resistors. Well, if we come back over here, parallel resistors, parallel components, have the same voltage across them, right? Because they share the same two nodes, they have the same difference in energy. So we know that this is going to be our voltage, and it's 10 volts. So that's pretty useful to us. Symbolically, if I was doing this, I would say this is IS, right? Because that's where the 3 mils came from. And we're going to multiply that by R1 in parallel with R2. Okay. We're going to revisit that in a moment, and I might do it differently than I did on the calculator. All right, coming back over here, we now know that we have 10 volts across all of these things. So if I want to find the individual current, I can say VR1 is equal to 10 volts divided by 5K. Okay, and that's really the voltage across R1. And we can say the same thing for VR. Wow. It's easy to screw up, folks. IR1. Volts over ohms is amps. I checked my units. I did it while I was talking. Granted, a little late. IR2 equals 10 volts over 10K. Check your units. All right, so that's V over R2. And we can figure that out here. 10 volts over 5K. So we've got 10 volts divided by 5K. And that's 2 milliamps. Okay. And 10 volts over 10K should be 1 milliamp. Yep. 1 milliamp. Okay. And we're good to go. Now, that's numerically. We did it numerically, and that's fine. But if you're applying the formula, you have to know where the formula came from. And we're following the same steps as we did before. So we have this little chunk here symbolically. So, right, so let's say symbolically, I don't know how to spell symbolically. Spell check has ruined me. The future is fantastic, except when it comes to spelling. So hopefully that's right. Don't tell me if it's not. All right, so symbolically, we want to find the voltage, and it's IS, and we've got this parallel combination. When I plug it in the calculator, I did 1 over the sum of the inverses of the resistances. But this is the case where, more often than not, you're going to see the current divider derived using the product over sum form. And there's a limitation to the product over sum form. And because we use that in the current divider, it becomes a limitation of the current divider as well. Okay? Recall that R1 in parallel with R2, we can write this way. But this only works for 2 resistors. Okay? If you have additional branches, then you run into a problem. You can't apply this one. Why did I write 3 there? You can't apply this one. Okay, so that limitation kind of gets adopted by the current divider because we're going to use this form to write the form of the current divider. So watch yourself with the current divider. Only 2 branches. Okay, so V is now IS, and I'll stick this in brackets. R1, R2 over R1 plus R2. Okay, so that's our V. Now if I want to go find IR1, let's start with IR1, I would take that V and I divide by R1. Well, here's what that's going to look like. We're going to take IS, we're going to multiply it by this product over sum. Okay, now I have to divide by R1. I like to put it out here. I think that's the easiest place to put it. We divide by R1. Now watch what happens. I'm finding the current through R1. That's why I divided by R1, but it's also why it drops out of the numerator. So if I want to find IR1, I take the current from the source, and again I have a ratio of resistances, but now the numerator is the opposite branch resistance. If I want to find the current through R1, I multiply by R2. And it's because that's the one that I'm finding the current through dropped out from the product over sum form. And that's the form for the current divider. Okay, so I just really want to emphasize this because it's easy to screw up. This is the opposite branch resistance. Okay, in the numerator. It's different than the voltage divider. So get that straight in your head as much as you can. Okay, IR2, it's going to look identical for the most part, right, I still have the sum of my resistances down here, but if I'm finding the current in R2, I need to multiply by R1. And that's kind of the payoff. Those are the forms of the current divider that we are going to work with. All right. So that's the payoff there. Now, we got to do two things. Be sure that, okay, we had these two things when we were dealing with the voltage divider. We kind of have to restate them for the current divider. So the first thing we want to be sure of is that the branches are in fact in parallel. Okay, the second thing we want to be sure of is that we are relating two currents. Okay, we want to relate two currents. And you know, if you're trying to get a voltage out of it, you got to do some other type of analysis. Don't use the current divider in that case. So we kind of have these same gut checks. Is it a current going in and a current going out? Yes or no? And are the branches in fact in parallel? Up here we can see that that is in fact the case. Now let's talk gut checks quickly. This is 2 milliamps here, and this is 1 milliamp here. They have the same voltage across them, so the lower resistance should have the bigger current. Right? So here's the lower resistance, and here's the bigger current. And the higher resistance has the smaller current. Okay, so that kind of tells me that I did it correctly, since they are in fact in parallel. All right, we're going to look at some examples of these and really work our way towards Kirchhoff's current law. I bet you can see it already, or you've learned it in other courses, but we'll go through how to write them in a consistent fashion so that we can ultimately start doing circuit analysis using Kirchhoff's current law. Okay, so stay tuned and good luck.